Does it show that it's, yeah, I think it's recording now. Okay, so this is our Zoom session to cover, intended to cover Module 6, but we may have some discussion on Module 5. And in fact, here's the notes for Module 5 that I've got here. And I'm assuming we want to start here if you have any questions.
Sure.
Anna, or do you want to start at Module 6?
5, yeah, I really struggled with 5. And I know that you and I were in email correspondence about a lot of it. I think that I was having trouble with the confidence intervals and locating the T-obs and finding different things on the chart in the book.
Okay.
And I know it seems pretty similar in writing to testing hypotheses like we were doing before our exam, but I don't know why this tripped me up so bad.
Okay, so would it be better? We can reference the notes here, or would it be better
Sure.
to go straight to the homework, to the WebAssign?
Oh, yeah, I did have trouble with that.
Would that help answer your question?
Yeah, I think so. And maybe that's just it. Maybe some of it's just me needing to do more practice problems. And that flow chart that you posted helped.
Okay, good. So if, let's see, this is the right assignment. Or we could look at a problem in the book too. But so, which one did you have a question with mainly?
I did okay on the first one,
Okay.
except that the first one I couldn't find the rejection region.
Okay.
I think I put 1.645. I can't remember what I actually put for that, but
Okay. Okay. Yeah. So in this problem, we're testing two population means. So WebAssign, the way they kind of set up some of these problems is they're not necessarily explicit about what the null and alternative look like. They might assume that you kind of know. But the alternative here, which I want to identify first, is, let's see, so does the data provide sufficient evidence that the rats exposed to a 5-degree environment have a higher mean blood pressure than rats exposed to 26-degree environment? So here, the difference in means, that they've got mu26 minus mu5. That's how they want to represent it. Those are the two population means that they want to say something about. So, so this would be, if mu5 is greater than mu26, then the difference in this order would be negative. That'd be right. This for the second number, for this number to be bigger than the first number, then their difference has to be negative. So the difference has to be less than 0. So this is going to yield a left tail test, which is why the rejection region starts off here less than or equal to. So so the rejection region, it goes back to test statistic, and we have a t-test statistic here. Okay, so we have a small sample size, and so if we want to look at,
yeah, I'm pulling up my notes on that too.
if you're in the situation where you have a small sample size, and by the way, this is the independent samples, right?
Right.
We have a small sample size. The standard deviations of the populations are not known, so this particular thing is kind of not realistic because we're not going to know sigma 1 and sigma 2. But the inference for mu1 minus mu2, or the difference of two means, when the variances are unknown, the more practical setting. We're not in a large sample setting with this problem. I think there were 6 data points uh,
Right.
for each data set. So we're in the small sample setting, and basically we have to choose between the setting where the equal variance assumption is reasonable or it's not. We have it. We called the first one the pool t-test. The other one was called the Welch Satterwhite t-test, sometimes called the separate variance t-test. But they both uh, have the first 2 assumptions are the same. You see that they both need independent random samples in normal populations. So those are both the same.
Right. It's just the variances that you have to, or I'm sorry.
No, that's right. Are the 2
Sample
population
variances.
variances, are they the same? And at this stage, really the best we can do um, is look at the sample variances and see if they're close.
And it said on within 2 numbers on the flow chart.
Yeah, if the larger one is not twice as large as the smaller, that's a rule. That's a pretty rough rule of thumb, but it works out not too badly. If so, if you have S1 and S2, if we go back to this problem here, let's see. I don't know. Did we compute S1 and S2? Um,
Um, let's see.
it's not.
Yes, for I think S1 I got 258.97. And then for but I think I had different numbers than you do.
Okay. But did you get the same? Did you get the right key statistic?
Yes, I wound up with negative 24.9.
Okay, and that was right. So let's just write down. So I'll just kind of ignore this that data we have here for now. You got 250. Now, was this the sample variances or the sample standard deviations?
I calculated both, but the 258.97 is the sample variance.
258.97 is the sample variance.
Uh-huh.
Okay, and what was the other sample variance?
272.4.
Okay, and those are really, that they're actually pretty close. If you take the square root of each of those,
They were both 16 point something.
okay, so yeah, so the larger is not a factor of 2 bigger than the smaller, and so
Right.
the pool t-test would be reasonable here. Now I do wish really in practice there should be some check of normality of the data. The WebAssign doesn't prompt you in that in the beginning of the problem. I wish they would, but I'd like for y'all to kind of have that just to remember, hey, the pool t-test, it has normality assumption for the 2 underlying populations. So really, if you were to try to do a pool t-test analysis in your nursing work down the road, you would want to somehow check for normality.
Okay.
But anyway, so we have a left-tailed t-test. So it's going to be negative T sub alpha. What was alpha here?
Okay. 0.05.
Okay, so negative T sub 0.05 and the degrees of freedom?
10.
Yes. Degrees of freedom is 10. So, let's see. I'm going to go to, I think I've got that chart somewhere here. Okay, so degrees of freedom 10, 0.05, 1.812. Now that's actually the upper tail percentile, so we want the lower tail, so it's negative 1.812.
Oh, because it's a left-tailed test.
Yes. Yeah.
Oh, and I just realized my mistake was I was looking at the view chart.
Yes.
That'll be a problem.
Yeah, and what was the z value? You got negative
Six, four,
1.645.
five.
Yeah, and if the sample sizes were if they were much larger,
Mm-hmm.
this t value would actually be pretty close to negative 1.645, and it really wouldn't make that much of a difference. But in this small sample scenario,
Sure.
it's pretty important to have the right t critical value. So anything less than negative 1.812 is going to
Is
be
in the rejection region.
yeah.
And so when it's a left-tailed test like that, I need to remember to make it a negative number.
For the t distribution, yes.
Yeah.
For the t and the standard normal, the left tail is going to have a negative value.
Okay.
Now in module 6, it's only introduced the chi-square distribution and the f distribution. Um, those are they start at 0 and go to positive infinity, and so there's really no negative values to consider.
Right.
So be mindful of that. So that's finding a t critical value, or find the rejection region.
Okay.
You want to continue through the WebAssign or go back to the notes?
I'm trying to think. I'm looking through my notes now and I think I was just having some trouble with the confidence interval, but I think that's just going to have to be practice.
Okay.
Your headset sounds a little fuzzy.
Let's see, is that better?
No, it's still kind of doing like an ocean wave sound.
Oh. How about now?
Now it's better.
Is that better? Okay, I don't know if it's a Zoom artifact or what. But,
Yeah.
So you can see the screen okay?
Oh, yeah.
Okay. Yeah, with the confidence intervals, I would practice, if you feel like you need practice, just find problems in the book that look similar to this one.
Right.
This was number 5, so maybe problems before and after it, or an example in the book.
Sure. And I did want to ask you, when you were setting up the alternative hypothesis, so I understand that we're doing mu 26 minus mu 5 because we're trying to find the difference in blood pressures. And I understand that 0 is D naught, but what is D naught?
So you're referring back to so like this,
right.
This quantity here.
Yes.
That really for our class, D naught is almost always going to be 0. In fact, I could probably say for all the examples that y'all will work through and problems will work through, and even problems in the test, that number will be 0. But
and that's just because we want to find out if it's negative or positive.
It goes back to it goes back to this situation, this bullet point here, that if you want to check to see if mu1 is bigger than mu2, you're checking to see if the difference is positive. Yeah, so you would say, well, is that difference positive? Yeah.
Right.
But sometimes you might be in a situation where you say, well, is mu1 bigger than mu2 by at least 3 units?
Oh, okay.
And so then D naught would be the number 3, and
gotcha.
Then would change your test statistics. And in some, this is actually a fairly common setting. Let's see here. In some drug efficacy studies, is the new drug, not is it just better than the old drug, but is it better than the old drug by at least 15%? Something like that. And so you're not just looking for an increase, a statistical significant difference, but you're looking for a particular increase.
Okay.
Yeah, so when you set up the confidence interval, just make sure, you've got this, for this problem, you're going to use, this is the formula here. Um,
And that's for the pooled test,
yes, that's for the pool that you want to do.
which is what we did. Okay, I see.
Mm-hmm. Yeah, and you had to compute this to compute your two test statistics in part A.
Right. Okay. We got 16.3 for SP. Is that, and that's pretty close to the standard deviations of those.
Yeah, SP.
Is that a way to check that kind of?
That's a good question. If so, SP is defined to be this, and if you look at it, well, it's if the sample sizes are the same, then this this is almost like the average, just the regular average between the two sample variances when you take the slow loop, because you have the coefficient out here in front is the same. But if the sample sizes are very different, then when you compute SP, it's going to give more weight to the sample variance that's associated with the larger sample size.
Okay.
So it's really a weighted average between the two sample standard deviations. And if the two sample sizes are pretty close, SP is probably going to be right in the middle of S1 and S2.
Okay.
If N1 is much bigger than N2, then you would expect SP to be closer towards S1 as opposed to S2.
Okay. And then we spoke over email about the other ones I had questions about, so I think I'm good on those.
Okay. For this whole assignment here?
Yeah.
Okay. So do we want to, Module 5 notes filled in? If you have any questions here, you can address those, or if you want to go to Module 6.
Let's go to Module 6.
Okay. So here's the notes. We can talk through them, or really, you're the only one here, so if you want to go straight to the left assignment, you can do that as well.
Okay. This one seemed to make more sense to me.
Okay.
I did have a question about the lower bound and the upper bound. There was a point where we were going through, and they on page 3, off to the corner right there, yeah, where they wound up being switched.
Yes.
I guess I just wanted to know when to do that, and yeah, I guess just when to do that.
Right. Well, in terms of what y'all really need to know, is this formula here.
Okay.
And actually, probably looking at the schedule, probably the week we get back from spring break or the week after that would be a good time for me to post what the formula sheet's going to look like for the next exam. But this is the sort of thing y'all would be given, that this is the lower bound for the confidence interval on sigma squared, and this is the upper bound for the confidence interval on sigma squared.
Okay.
It seems counterintuitive in some sense, at first look, that the upper chi-squared percentile is in the denominator here, and that the lower chi-squared is in the denominator here. And that's actually a consequence of the mathematical derivation of the interval. And that's what I tried to do at the top of this page. This is page 3. Was I said, well, if we start here, if we start that n minus 1 times s squared over sigma squared is distributed chi squared with n minus 1 degree of freedom, then we can set up a probability statement that's over here, and that probability statement would say that, well, that quantity is going to be bounded below by a lower chi-squared percentile and an upper chi-squared percentile. And then the rest of this, going through all these expressions, is just a matter of getting sigma squared by itself in the middle of the two inequalities. And so
okay.
It's an algebra game, really. And the first thing that we did was we divided everything throughout by n minus 1 times s squared. And so that goes away in the middle, but it pops up over here, and over here.
Mm-hmm.
Now, but what we want is we want sigma squared in the middle, not 1 over sigma squared. And so we flip everything. So we flip everything into inequality, and if you do that, and that's kind of what I tried to argue to demonstrate up here. If you flip, if you take the reciprocal of both sides of the inequality, then the inequality direction needs to change. So
Okay.
what was less than becomes greater than. And so then I said, well, let's just, instead of this number being bigger than this number, usually you read from left to right as smallest to greatest. And so I just said, well, let's make it look like, okay, sigma squared, yeah, it's going to be less than this number. Let's just write it in a way like that, which makes it a little more conventional
Okay.
expression. Anyway, this whole discussion here is kind of more for mathematical curiosity. If you're wondering, if the student's wondering, where does this interval formula come from? Well, it starts off with this ratio follows a chi-square distribution, and based on that, we have a probability statement, and then using some algebra, we ultimately get down to this, and that gives us the lower and upper bound for an interval less than sigma. So the big takeaway would be, if you want to memorize if you want to work through this derivation, you certainly can. It requires some algebra in there. But I'm really more concerned with y'all knowing this formula here. I'm going to give it to you on the midterm, or the second exam. Knowing that formula, knowing how to use it, and then knowing how to interpret the results of that kind of competency.
Okay.
Now, one thing that was kind of interesting with WebAssign, in fact, pages in the notes here, 1 through 4, 5, they deal with, these pages deal with inference on a single population variance, either through in this setting here, a confidence interval,
Mm-hmm.
or the hypothesis test, which is here's the definition. I say all that. This is important. It's in the notes, and it's in the book. It's in the margin notes, but it did not make it. The WebAssign group that made the problem for some reason did not include a problem on a single day. So I put a practice problem that I think y'all should go through.
Okay.
That's part of that practice problem that deals with a confidence interval, and I think a hypothesis test on a single population. WebAssign, the two problems there really focus on the ratio of of two variances. So inference on two population variances.
Instead of a single.
Right.
Okay. I had a question about for that example on page 3. So I followed through down to where we got negative 12 minus or 12 minus 1 times 0.047 squared. But when I calculated both of those, I didn't get either of those numbers.
Okay.
I don't know what I was doing wrong.
Did you take the square root?
I did, yeah. I got like 3.31 for the first one, and
Okay.
I don't know, I was doing all kinds of crazy stuff.
Let's see. So if we let's just take the lower bound here. So if we have the square root of 11 times 0.047 squared, the 21.92 is okay.
Mm-hmm.
Okay. So if we want to, let's just compute the numerator first. I'm going to take 11 and then.
Oh, that's why. Why did I write down? Oh man, Dr. Riggs, I am all over the place. I wrote 29.92. That. What is happening?
That's all right. Yeah, everybody. It's time for spring break, huh?
I guess so. I'm fried.
Let's see. So now with 21.92, do you see how you get 0.0333?
21.92. Let me check this. I sure do.
So that worked out?
Yes.
Okay, good. What was your upper bound 0.0798?
Yes.
Okay. Good. All right.
Well, so that solves that mystery. And I was pretty okay on the rest of these notes.
Okay.
And I was watching some YouTube video, and this guy was using the F distribution to figure out the variance if they were equal or not.
Yes.
Does that sound correct?
Yeah. Was he testing two variances to see if they were
Yes.
two population variances were equal? Uh-huh.
Okay. But so I guess what are the general takeaways I should have between the difference between F distribution and chi-squared distribution?
Yeah, that's a good question. So for us, the chi-square distribution right now is what's used in inference on a single population variance.
Okay.
But if you've got two population variances, then the distribution that plays a role in doing inference is the F distribution.
Oh, okay.
And so there's these distributions, they come from, they have kind of a mathematical basis and a theorem that I just present here. But ultimately, I want to be able to use the F distribution to do a test in the compensating ratio.
You sound kind of far away.
Oh, is that better?
Yes, that's better.
Okay. So the in statistics, whenever you're doing an inferential procedure, either hypothesis test or a confidence interval, a test statistic or some percentile, some aspect of it is going to involve a probability distribution. And for what we had, say, in Module 4 and in Module 5, we're really we just had to deal with the normal distribution and the cubic. But as we kind of expand the kind of the methods that we can uh, cover in terms of doing inference, then that's going to naturally pick up other distribution, physical distributions. It turns out there's a whole host of there's tons and tons of distributions that are out there. These are the popular ones in particular because they're connected to um, these same statistical procedures that are used in a lot of different disciplines. But um, I know from the student's perspective, you see all these distributions and you think, well, what's the point of it? They have a role and kind of seeing exactly where their role comes in. You have to take a mathematical.
Right.
But the big picture for us in the applied stat course is that different statistical methods will require the use of different distributions.
Okay. I did have a question. I know you posted something about WebAssign 1 and 2.
Yes.
It's doing that ocean thing again, or the white noise.
Okay. Is that better?
No.
Oh man.
It was fine when we weren't recording. I don't know if there's reverberation because we're recording now.
Shouldn't be. You know, I'm going through this Purpose tablet, and I've always had a little trouble with its audio.
Yeah.
Is that any better?
It is, yes.
Okay. Yeah.
I know you posted that about the first or the 2 problems on WebAssign. I didn't get to look at that yet. But I did just notice on the first WebAssign problem, it was like it was flipped what they wanted us to figure out as far as finding F in the test statistic. It was S2 squared over S1 squared.
Yes.
But that wasn't what my note said, and I did it, and I got the right answer. But I guess I was just kind of wondering why they did that, or.
Yeah, no, good question. Did you compute S1?
Yes. For S1, I got 3.35.
Okay.
And S2 was 4.74.
Okay. The reason that WebAssign is prompting you to do S2 squared over S1 squared is because S2 is larger than S1. The common approach when doing a test on the ratio of P variances is to take the larger divided by the smaller.
Oh, okay.
And if you go back to the notes, let's see if I can reference it in notes. In the test of hypotheses, we either have a two-tailed test or just a right-tailed test. Notice it's
right.
not a left-tailed test. And the reason, and you could make a left-tailed test, and some different books would have a left-tailed test and have sigma 1 less than sigma 2. But really, you could just switch what you're calling 1 and 2, and then a left-tailed test would become a right-tailed test. As long as you make whatever is here, the sample variances are also ordered to where one sample variance is larger than the other sample variance. So that you can use, ultimately, so that you can use the upper part of the F distribution to get your rejection region for what is right tail kind of test.
Okay.
I don't know, does that kind of answer it?
Yeah, I guess my concern is in future problems or on an exam, is that something I would need to implement as far as thinking, oh, S2 is bigger than S1, so I need to flip those.
Um,
Or is that something you would ask? Like the way that it's prompted here in the WebAssign assignment.
yeah, I would. I might not. I might present this to a few samples such that it's almost up to your discretion to what you want to call one and what you want to call
I see.
two.
Okay.
In this
Because it doesn't
problem,
matter. Yeah.
you might have new drug also, and so, but if you when you go to the computation, yes, you will want to have the larger sample density as the one in the numerator
Okay.
for the reason if you just go to a right tail, X percentile to a right tail.
Okay. Um, and then, so it looks like I got my rejection region down to reject H naught if F is greater than or equal to 0.3145.
So for number one,
Uh-huh.
okay, so let's see. So it's kind of so what were our degrees of freedom? Enumerated degrees of freedom.
Let me see. Degrees of freedom, they were both 9.
Okay, so DF1 and DF2 are 9. So we, we're going to want to find um,
Oh,
it's going to be in the right tail.
right. So, okay, so when I looked that up, this was the question I had. Okay. So when I looked it up on the chart with F sub 0.05, 9, and 9, it was 3.18. And that was what I guess it wanted me to figure out in the question. But in our notes, we did 1 over F sub 05, 9, 9. And it didn't want me to do that in the homework.
Yes, let's see. You talking about right here?
Yeah.
Okay. Yeah, this was a
Two-tailed?
two-tailed test, and so excuse me, we had to consider a lower F percentile that would start the rejection region in the left tail, in addition to the upper tail percentile.
Okay, so only do 1 over what you find if it's a two-tailed test.
Well, if the way that a better way to think of it is the table that the book did is upper tail percentile. And so if you can couch the problem as if it's a right tail test, if you can somehow couch the problem as a right tail test, that's kind of what WebAssign is doing. You get you the larger of the central density divided by the smaller of the central density. If you can do that, then you don't have to deal with the right tail. You can use the execution. But if there's a situation where you might need lower tail percentile, then you have to appeal to this relationship that says any lower tail percentile is 1 over kind of the F, so this is F sub 0.95, it's F sub 1 minus 0.95 or 0.05, and then the degree of freedom of switch.
Okay.
And so, and notice when you found 1.94 in this problem, we didn't switch the degree of freedom. We did 30, 0.4, but this one is 24 on the 30. And
Oh,
so we
I
looked at a
see.
different part of the table, and that in turn gave us the lower F percentile. It really, in terms of the notes, uh,
Okay. That makes more sense.
yeah. So that part is referencing that photo.
Oh, okay.
If you want a lower tail percentile, you use that expression there. That you take the upper tail percentile, divide it into one, but also switch to the
Okay. That makes more sense.
and really, um, so that's somewhat useful. That's just using a table, and it helps you get lower tail percentiles in addition to upper tail percentiles. Out in practice, if you were to use Minitab or Jump or even Excel, you would get those. Um, you would just let them find those for you. But coming back to this one, did you find this quantity okay?
Yes, I did.
Okay.
So it was 3.18 in the chart.
Okay. 3.18. So anything larger than that is in the rejection region.
And I
Then,
guess F I got 4.01, so it was in the rejection region.
okay. So when you put 3.35, actually 4.74 squared over 3.35, so you get 4. What did you say?
Is that right?
2.0.
Oh, 2.002 was what I got for it. I'm sorry. For
Okay.
that.
Yeah. Okay. So this. Let's see. Let's look at the F table. Make sure we got
Okay.
F. So degrees of freedom are 9 and 9, and the alpha is 0.05. And okay, so see. Did I? Is it on an earlier page?
Um, let's see. So degrees of freedom, it was 9.9. Oh, yeah, it was on like some two. Yeah, this chart kind of confused me too.
Yeah, I mean it's a monster chart.
And sometimes degrees of freedom 2 are on the left, and sometimes they're on the right. And
Yeah. So so I think this would be the last page right here.
right.
Look,
Okay. Yes. 9,
9,
9
and
point 0,
the alpha is 0.05. So yeah, I see it there.
3.18.
Mm-hmm. Okay. So good. So we would fail to reject the null hypothesis.
Okay.
Uh, so you would fail to reject the null and conclude there is not. So how would that there is not? Let's see. Either going to be B or C, or B or D. Fail to reject it and conclude basically when you fail to reject a null, you cannot. You're not. You don't get to the point where you have significant evidence for anything.
Right.
So it can't be B.
Okay.
But D is equal to H I. Fail to reject H I complete there is not significant evidence that portfolio two has a larger variance in portfolio one. If you wanted to, just to be clear here, if you were thinking about what do the hypotheses look like, this is really what That's the alternative hypothesis at sigma 2 squared
Okay.
is greater than sigma 1 squared. And if you want to rewrite that, you think, well, what's the deal with ratios? Well, that's the same as the ratio being bigger than 1. If one number is bigger than another, then that's equivalent to that larger number divided by the smaller number being bigger.
Okay. And I think that's maybe why I had an easier time with this, because this is more like the hypothesis testing we were doing previously, it kind of feels like,
Okay.
as opposed to comparing the what we were doing in Module 5. Is it more the central values?
Yeah. Um, we were comparing most of the time two means in
Yeah.
module 5 or two medians. But if you in module 5, if you have dependent samples, then you're actually just doing inference on a single population mean difference.
Hmm. Yeah, and I didn't get to number 2 yet, but I'm sure I
Okay.
will.
Okay. But just to kind of give you some insight into number 2, I did write uh, you might want to reference that email that I
Okay.
responded to. But for number 2, the kind of the big overall picture is they are in part A. They're doing uh, they're they're doing inference on two population means. So they're looking at mu1 minus mu2, however you want to designate that. But um, that's what part A gets at. So that's actually a module 5 idea for
Okay.
last week. And um, that in some settings, that's the more important question than a question of how the variances compare. And the variances uh, are important for stuff in Module 5 because in Module 5, you recall the pooled t-test had the assumption that um, the two population variances are the same. And so one way to ask the question, should I use a pooled t-test, is to do to test, well, are the two population variances the same or are they different? And if you fail to reject this null hypothesis, then that might be evidence to go forward with the pooled t-test. So that's
Okay.
actually a little bit better approach than asking a question: is S max, is it is is it more than 2 times S min, the smaller of the two? Is, is the big,
Okay.
so that's a connection with module 6 and module 5 that this is sometimes called a pre-test using the F-test on the population variance to kind of pre-test if full pre-test is appropriate to begin with. Now, um, all that said, actually in part B, uh, they actually want you to test if zone 1 has a higher variability than zone 2. So they're not doing a two-tailed alternative. They're actually doing an alternative that would be, sigma 1 squared greater than sigma 2 squared. This is the one-tailed alternative.
Okay. Okay, and then I'll do those practice problems too, and that'll help.
Yeah, good. And I've got videos for all but one of those, and the one I don't have a video for, um, I've got a PDF that has the solution to it. And if you have questions about that PDF or even those videos, I can try to answer questions. You may want to look at the problems that are on web design, reading the practice problems, and see which ones are odd. or odd numbers, and then use those, work through those, and then check your answer in the back of the book. I think the odd ones are listed in the back of the book.
Okay.
So
Um,
yeah, more
are,
practice typically the better off.
yeah. Um, are there any, I guess, online resources or I guess maybe YouTube channels you swear by just for so over spring break I can kind of.
I can. There's, really, the Khan Academy.
Uh,
You've heard of Khan Academy.
yeah. Okay.
They typically have good stuff, but honestly, I haven't looked at what they you know, really much of their stuff. So,
Sure.
you could, you could do that. Um, when you're watching videos, you could do that. It seemed like I saw a guy one time. I think he was looking at my other computer. Well, I don't want to.
Refer anybody without.
I'm hesitant to do that.
Yeah.
There's now. I will. Uh, I can. I do have a colleague, a former colleague. I have a set of notes. That would be PowerPoint that I could put online as well.
Okay.
That would be more lecture stuff, and like stuff that he used in lecture.
Right.
They're actually really pretty good PowerPoints. One of them is a professor here. He's still here. The other one I've used before, or that I've let students use as a resource, is for a professor at Texas Tech. Um, let's see. Then let me think on that a little bit, because I had some former classmates that are at a medical school in Arkansas, and they might have some resources
Okay.
that
That sounds great.
would be tailored towards medical science.
Okay, cool. And then yeah, and I'll just keep doing practice problems and look up things on the World Wide Web over spring break.
Yeah. Let me see if I can try to find it. I'm gonna make a note of that.
Sure.
Do that tomorrow morning. So in particular, you're looking for videos as opposed to PowerPoints or any of it?
I honestly whatever just sinks into my brain. I'm open to anything.
Okay. Well, let me ask you this: when you go through the book, when you're reading the book, is
So,
overwhelming or
well, my problem with the book is that sometimes I feel like they find such elaborate studies and they can go on about the studies for like a page or a page and a half when I just want to figure out why I need to do the problem and what I'm looking for,
mhm,
so sometimes I just kind of feel like the book gets really wordy and maybe gets away from the main point of
right,
what I need to be learning.
right, okay. Um, Let me see what I can find, uh, and I think I can find something to take before spring break. Either
Okay.
at least a set of PowerPoint files, maybe uh, um, you
They
know,
just might be more direct.
video
Um,
references.
yeah, just because I feel like just for learning, since it's our first time learning some of this stuff, um, sometimes the book can just have really elaborate, data or
Yeah, the problem setups can be they can be complicated. A lot of nuances and
Right.
And they kind of, I think they do that on purpose to make you think that when you tackle a problem and you use statistics as a tool, it's really you really need to be thinking about a lot of different situations. You need to be
Right.
thinking from a lot of different points of view. Um, even for us, one course, I would say, uh, I don't know what the nursing faculty would say, but I would say that one course is really not enough to go and do a lot of statistics beyond after you take the course, unless you get a book and you just continue to learn and go through it and almost
Right.
master the book we have, and then I would say, yeah, you could go through a lot. But for someone that does one course in it, I think you know the objective is we ought to have an exposure to statistics, the, the main methods or basic methods, and how they can be used, what's some assumptions, what are the assumptions that are important to it, what are some pitfalls, and if you're listening to somebody that's using statistics in a scientific journal or a medical journal, then you can have some sense of judging their work. Um, Not that you would have to necessarily reproduce the statistical work they did, but that you would have an eye for understanding what they've done statistically
Right.
and judging it a little bit. Um, really. If you take
Yeah.
if you take I've done this before, but if you take, say, if you buy a prescription drug and the pharmacist gives you the big handout on that particular drug, it's usually a piece of folded. The one I've gotten before was a folded piece of paper, and you unfold it, and it was like this big map. Um, and within there was a lot of there was a fair amount of statistical terms that by the time you get to the end of this course would be somewhat accessible for y'all. So anyway, it's it's all over the place, and I've tried to state that throughout the videos, but it's even on pharmaceutical safety
Right.
data sheet sort of thing. Um, but yeah, so I kind of just have it there. I'll look for videos and PowerPoints
Okay, great.
and other resources. Any other questions you got?
No, I mean that was really it. And then I'm gonna try and tackle um, question number 2 on the homework tomorrow. And I know you posted some stuff on that. So,
Okay, good deal.
but yeah, thank you so much for your
All right,
time.
you're welcome. You're welcome. Y'all have a good night and a good spring break.
Okay, have a good spring break, Dr. Riggs.
Bye bye.
Okay, bye.